So, good afternoon, everyone, and welcome to this Spotlight Talk. I'm Giorgio Veronesi, President of the European Federation of Chemical Engineering, EFC. I've been in the board of EFC in various positions for over 9 years, and currently I'm in my second term as president. I'm a chemical engineer by training, graduated in Padua, Italy, and I've been spending the whole of my career in the engineering construction business, involved in many projects, mainly abroad, with the several assignments overseas. I'm very happy to be involved in the introduction of this webinar on electrostatic charging of liquids, fundamentals, risk, and safety measures, organized by the Working Party on Static Electricity, and I'm looking forward to participating to it. Let me say something about the Spotlight Talk series. This is now our 6th year of the Spotlight Talk initiative, which started in 2020 to keep together the community during the COVID pandemic. The success of the initiative convinced us to transform the series in a regular feature of the EFC program. So we have now one Spotlight series in odd years, like 2025, and two in even years. This spring, 11 of our working parties and sections, chemical engineering applied to medicine, sustainability, chemical reaction engineering, process intensification, comminution and classification, mechanics of particulate solids, fluid separation, polymer reaction engineering, static electricity, this one, crystallization, early career chemical engineers, are delivering over 2 weeks 10 webinars with talks on specific topics by leading industrial and academic experts. The complete program is available on the EFC websites. EFC promotes scientific collaboration and supports the work of chemical engineers in 27 European countries, representing more than 100,000 in Europe. EFC working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFC activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. In particular, I would like to inform everybody about the two EFC events relevant to static electricity and electrochemical engineering that will take place in Italy this year. The Electrostatic Conference in Bologna from 9th to 12th of November, which Pedro will talk about later, and the Electrochemical Engineering School in Cagliari from 22nd to 26th of September, sorry. You can see relevant details both on EFC website and on IDIC website. IDIC is the Italian Association of Chemical Engineering. Before concluding, I would like to thank all the people who work hard inside the working parties, the sections, and EFC in general for this initiative to happen and be successful. In particular, many thanks to EFC Martin Pou in Toulouse, who did most of the conceptual setting up and practical activities, and she is here today as well. I'm taking this opportunity to inform you that the EFC board has decided to award to Martine the prestigious Dieter Behrens Medal for her contribution to chemical engineering that will be delivered at the European Conference in Lisbon in September. So thanks, Martine, and congratulations for this well-deserved award and important recognition for your work. I thank you for your attention and wish all the speakers and the attendees a fruitful and successful webinar. I would then give the word to the chair of the Working Party Static Electricity in Industry, Professor Pedro Llovera-Segovia, from the Polytechnic University of Valencia, to start the works. Pedro, the floor is yours. Thank you.
Thank you, Giorgio, for your introduction. It is an honor to have you with us today. So it's my pleasure to chair our 6th EFC Spotlight Talk on electrostatics, which is a part of the 8th EFC Spotlight Talks. So I am electrical engineering by training. I've been working on electrostatic properties of materials, electrostatic diagnostic of industry facilities, offices, commercial areas for more than 20 years. And I am also teaching at the Polytechnic University of Valencia and making research with the Energy Technological Institute IT in Valencia in Spain. Of course, I would like to thank EFCE for organizing this webinar and giving us the opportunity to show our work, especially to Giorgio for his presence today, but also for Martin for her excellent work organizing the Spotlight Talk, a task that is by no means easy. And also, I would like to thank the IT, the Energy Technological Institute for helping me working on electrostatics. And of course, all of you for attending this webinar from many countries worldwide. We are happy to see that it attracts attention to many people, and we hope it will meet your expectations. Because one of the aims of this webinar is to build a scientific and technical, let's say, electrostatic community. So I strongly encourage you to participate with your questions during webinar. We'll be very happy to answer both technical and specific questions from specialists, but also fundamental questions from those who are starting in the field and who, of course, are very welcome today. For organizational reasons, you are not allowed to use a microphone. You need to write the questions in the Q&A section. You can write them during the presentation. I will collect them and read them at the end of each talk. And probably, if we have time, maybe we can have an additional time for question at the end of both presentations. Today we have, I'm sorry, I will share my screen. It's okay now? Yes. Now I'm sharing. So today we have two very interesting talks on static electricity. And the first presentation will be given by Professor Thierry Paillat from the University of Poitiers about charging of liquids, fundamentals, material properties, and measurements. And the second talk will be given by Dr. Jeremy Smallwood from Electrostatic Solution. He will make an overview on risk and standard recommendation, and he will also give some example and cases, especially focus on liquid charging. So we will start with fundamentals and finish with practical consequences. As Giorgio mentioned before, this is a part of the EFCE free webinars. Here you have the full program. We are nearly at the end of this spring session. Tomorrow you also have some presentation. I think the last one is very interesting for young chemical engineers. So I recommend it if you are listening to this, attending this webinar. And if you miss one of them, you can find later on the EFCE YouTube channel this presentation. You can find all our presentation on electrostatics. This is the list of our last 4 years. We have addressed measurement, safety, hazards, comfort, application, particles, and now the missing topic was liquids. So today we will talk about charging of liquids. Our working party, which complete name is Static Electricity in Industry, is devoted to problems and application of static electricity and process. We bring together many experts from Europe and also from countries outside Europe to promote the research activity and the knowledge diffusion of electrostatic in industry. Of course, static electricity may seem an old, relatively well-known topic, but it is very present today, and I would say that not always very well understood. For example, liquid charging is quite complex, and I think today we will understand better what is happening in pipes and pumping of liquids. We talk about risk, of course, but not everything in electrostatics are risk. There are also applications such as precipitators, separators, electrospinning, electrohydrodynamic flow control, applications in the aerospace industry, high voltage, biology, etc. You can find information of our working party at our webpage or join our LinkedIn group, which is quite new. So we're starting with this. And as general activities, I would like to mention the general conference, the ECC in Lisbon in September. And of course, as mentioned Giorgio, our electrostatic conference is a conference we organize every 4 years. There's another let's say, sister conference organized by IOP every 4 years, which is shifted 2 years from us, and we are coordinated. This year, we will organize it in Bologna, Italy, which is a very nice place to visit and to learn from electrostatics. It is organized by the University of Bologna and by IDIT. The chairs are Dr. Ernesto Salzano and Giorgio Veronesi. We are currently preparing the proceedings and receiving papers. So we are now closing the phase the phase of sending full papers, but you can still send full paper even if you missed our previous call for papers. If you contact us, you can still send a full paper before 31st May, before the end of this month, to the Journal of Electrostatics. If you want to have your paper published at the journal, of course, it will follow a review process. But if you want to present a work on the conference without publishing at the Journal of Electrostatic, based on an abstract or a short work, you can still send papers during the next month. You have all the information in our web page about the conference. Here you have the contact information if you wish further details from the conference. I think it's a very interesting conference because of the multidisciplinary approach and the contact with many experts in the field that always bring very new ideas and a clear comprehension of electrostatics. Okay. We are also happy to promote the ESA annual meeting in Ontario. We have some links with the Electrostatic Society of America. They organize a conference in June. We always promote each other. In the end, the electrostatic community worldwide is not so large. We all know each other. So we are also happy to announce this conference and hope to meet you in Canada. So now let's move to the presentations. I would like to introduce now our first speaker, Professor Thierry Paillat. The picture is quite old, I'm sorry. He's from the Faculté des Sciences Fondamentales Appliquées at the University of Poitiers. And he's working at the university since 1998, but since 2016, he's full professor at the Prime Institute, Poitiers. His research interests are in electrostatic hazards by flow electrifications or fluids and fundamental aspects of electric double layer that he will explain now. Before giving the floor to Thierry, just remind you to ask your question in the question section. Don't wait until the end of the talk. If you have a question, you can write it immediately, and I will collect them and read them at the end of the talk. So now, yes, Thierry, the floor is yours.
Okay, thanks a lot, Pedro. So I run up. Is it okay?
Yes.
Okay. So good morning, everybody. So I would like to present my talk about the electrical layer and the flow rectification phenomenon in the context of electrical engineering. This work is proposed by myself, Thierry, with the collaboration with Paul Leblanc and Gérard Touchard coming from the Poitiers laboratory. So after a brief introduction of the phenomenon, I will describe the electrical layer, its different properties, and we will modelize it and the flow rectification phenomenon in link to the electrical layer. We'll introduce the electrical layer in the electrical engineering for finally propose some measurements which allow to determine the property of the electrical layer. So consider this small setup in which we have two reservoirs, the inlet reservoir, the outlet reservoir. The inlet reservoir is filling up the liquid, and we impose through duct the liquid flow from the inlet to outlet reservoir. If the two reservoirs are insulated, and if we measure the potential difference between these two reservoirs, we will observe an increasing of the potential between the two reservoirs. This is the flow rectification phenomenon. This phenomenon is due to some physical which appear at the interface in the duct, named the electrical double layer. So what is the electrical double layer? Ethical level layer is a phenomenon which occurs at all solid and liquid interface, which polarize the interface of two opposite charge areas, one inside the liquid, another one inside the solid with opposite sign. The first model which has been proposed of ethical level layer is this one proposed by Helmholtz, in which he considers the ethical level layer as a capacitor. More than 90% of the polarity of the ethical level layer is negative in the liquid and positive in the solid. A more realistic model is proposed by Stern, in which he considers in the liquid the diffusion, because in fact, due to the diffusion, the charge in the liquid diffuse in the liquid bulk. Stern distinguished two sublayers in the liquid, the compact layer, so close to the interface that the charge are kept to the solid. They are not able to move by a liquid flow, for example, or electric field. The thickness of the compact layer is about a few angstrom. From the compact layer in the liquid bulk direction, we have the diffuse layer. The diffuse layer is composed of charge we can move, for example, coming by a liquid flow or by an external electric field. The diffuse layer thickness is associated to the bi-length, but we'll discuss more later. So for describe the ethical level layer, different parameters may be introduced. First, in ethical engineering approach, we will consider the spatial distribution in the liquid. Commonly, we neglect the compact layer. In the diffuse layer, classically, the spatial distribution is maximum at the interface and decreasing according to an exponential law in the liquid bulk direction. At the equilibrium of the ethical level layer, we introduce the spatial density at the wall at the equilibrium. This number for ethical engineering is a signature of the solid-liquid couples. Typically, for dielectric liquid, the spatial density at the wall is about 10 to minus Coulomb cubic meter, while for conductive liquid, it can reach about 10 to 4 Coulomb per cubic meter. Classically, in electrical engineering, they more make a focus about the potential distribution. Potential distribution is also in the liquid, in the diffuser, take an exponential law decreasing, but they introduce an interface precisely at the sharing place, the zeta potential. The zeta potential for aqueous solution can be estimated considering only electrical property of the liquid, in which we have the liquid conductivity, we have the diffuse layer thickness, and also the liquid permittivity. Classically, the zeta potential averages between 100 millivolts. These two parameters, the zeta potential and the spatial density and interface at the equilibrium, are linked by the Poisson equation. Other parameters that's important to introduce ethical level layer is the diffuse layer thickness, the bi-length, is a classic expression, but this the bi-length could be also explained according only electrical property of the liquid, in which we have the liquid permittivity, we have ionic mean diffusion coefficient, and also liquid conductivity. The bi-length is measured controlled by the liquid conductivity, because effectively for conductive liquid, the bi-length take a value about a few angstrom, about the ready or the ion spaces, and for conductive dielectric liquid, the diffuse layer thickness can reach about a few millimeters. The last parameter that's important to control in ethical level layer is the formation of each one, because effectively it takes a few seconds or few hours to be developed. It mainly depends on the liquid. It depends of two times. It depends on the relaxation time. Relaxation time is allowed to describe the time of diffusion of molecules of ions near the interface in the liquid bulk and stability. And we have to consider also the chemical time. Chemical time will allow to control the time needing to create a charge at the interface due to chemical reaction. Effectively, different model proposed, or genesis has been proposed to describe the electrical level layer formation at the interface. In electrical engineering, all the models are in agreement to assume that it is some impurities in the dielectric liquid, which are at the origin of the electrical level layer. A few ppm or ppb concentration of impurity are enough to produce the electrical level layer. The first model that we've confirmed is the absorption model proposed by Stern. Absorption model suppose effectively that we have impurities in the liquid, which are partially dissociated in positive and negative ions. And one species in this simulation, the negative species, is adsorbed at the solid surface. Consider this situation. We have an excess of positive charge in the liquid and negative charge in the solid, and we polarize the interface. The charge transfer is a charge transfer coming from the liquid to the solid. Other model has been proposed is the corrosion model. Corrosion model consider also the dissociation of ionic species of some molecules, impurities in the liquid, but at the same time, at the contact of the liquid and solid, we have a chemical reaction or corrosion reaction from the solid, which from neutral species from the solid, they create two ion species, negative and positive species. We consider that positive species diffuse in liquid and react with negative species coming from the dissociation of impurities in liquid. This induces new neutral species and also an excess of positive charge in the liquid and negative charge in the solid. We have also polarized the interface. Globally, the charge transfer is from the solid to the liquid. Other model has been proposed is model which is a mix of adsorption and corrosion model. So, considering the different elements, we are able to propose a modelization that we call double layer, and especially of the diffused layer. For that, we have to introduce all the different equations of motion of ionic species. So we have the diffusion flux, controlled by the gradient of the concentration of the any species. We have also the conduction, the migration, linked to the potential gradient. And finally, we can also introduce the liquid motion by the convection flux due to the velocity of the liquid. In this context, we have a global equation of the motion of the liquid of the species E in the liquid, which could be explained in terms of current density. At the current density expression, we have to consider the conservation equation, in which we have the two terms, the temporal terms and the spatial term, and all these equations must be written for the different species present in the liquid. For simplify the situation, the problematic, we have considered only one positive and negative species, which could be considered as an average or the representation of all different species present in the liquid. We associate P for positive species and N for negative species. So if we introduce a mean coefficient diffusion for the positive species, the number of positive species in liquid, we have thus a current density explained for the positive charge and a conservation equation also for positive charge. The same expression could be explained for the negative charge. At this time, we will introduce some from other parameters, the spatial density. The spatial density is only the difference on the number of positive charge and negative charge present in the liquid. D0 ionic mean coefficient diffusion. The liquid conductivity within the addition on the number of positive charge and negative charge, and alpha. Alpha is a constant that is important for the development more later. Alpha is usually equal to 1 and is induce the difference between the positive and negative ion diffusion. As this equation, we have also to introduce effectively the Poisson equation, which allow to make a relation between the spatial distribution and the potential distribution. For simplify the modelization, classically, the equation are dimensionalized, uses some reference number, uses the propriety of the diffuse layer, in which we have the diffuse layer length, we have the electrical conductivity, the formation time of the diffuse layer, and finally a spatial density. This whole equation conduct to have a system of unknown equations which no analytical solution is currently identified. A partial solution could be proposed only by a step-by-step resolution that introduces some simplification. So I will propose to introduce this resolution of the system. And in the first step of the analysis, we will consider that we have no liquid flow. And also, the electrical Llovera have not evolution versus time. It is at the equilibrium. And we introduce the script pipe infinite for present system to symbolize the equilibrium of the system. So in this context, the five equation is limited to two equations, in which also no analytical solution can be proposed in a global situation. For have an analytical solution, you have to introduce one more simplification, named the weak spatial density and wrong spatial density. The simplification is introduced here, in which you have to make a comparison between the spatial density and alpha. Alpha is quite equal to 1, so we have to compare rho considering the alpha. In the case of the spatial density is lower than alpha, it's the hypothesis named the weak spatial density. The system can be simplified like that. Weak spatial density means that the liquid conductivity is not affected by the concentration, the charge distribution in the diffuse layer. It's typically true far from the interface, in which effectively the electrical conductivity of the liquid is properties. The opposite hypothesis is strong spatial density. Strong spatial density means that the spatial density is higher than alpha. And this hypothesis is quite true near the interface. So consider one of these hypotheses. We are able to propose an analytical solution of the charge distribution. For this talk, I have presented a solution for geometry, a circular geometry duct, in which we assume a weak spatial hypothesis in all the volume of the liquid. In this situation, the spatial distribution is given by this expression and also the potential distribution, in which he evaluates according a Bessel function of zero, modified Bessel function of zero order. It's interesting to analyze this expression, in which is controlled by three terms. The first term is alpha. Alpha is quite equal to 1. You have no significant effect. We have the radius of the duct. We have the diffuse layer thickness. The diffuse thickness control the charge distribution in the deep of the liquid. And the spatial density at the equilibrium at the wall control the magnitude of the electrical double layer. In the second step of the demonstration, we will introduce the velocity. We put the liquid in motion by especially a laminar flow. So we consider also that the diffuse layer is at the equilibrium and will transport by laminar flow. We transport the diffuse layer by a laminar flow. So I would like to make a small animation. So in this context, the diffuse, I don't know it's working, yes. So in this context, we have, due to the laminar flow means that we have only one direction in the velocity. The charge are only transport at the same distance from the wall, but with a velocity depending from the distance on the wall. So if we come back to the setup that I described at the beginning, if we determine, as we call, the streaming current is the current that we measure by collecting the charge in the outlet reservoir. This streaming current is only an integration in the surface of the duct of the spatial distribution cross the velocity profile from laminar flow. We can also associate a streaming current, as we call the convective spatial density, which is only the streaming current divided by the liquid flow. After integration of this integral, we can determine swimming current evolution and also the convective spatial density. It's important to note here that for fully developed diffuse layer convected by laminar flow, if this one is fully developed, sorry, it is directly proportional to the liquid flow rate, the mean liquid flow rate. And Q is non-dependent, is a constant of the diffuse layer. It's interesting to analyze the different terms in this equation. Sorry. And for example, we consider a couple in which you have the ethical level layer which is developed like that, the maximum interface and decrease in the liquid bulk, and we transport it by a laminar flow. If we imagine that we are able to modify the liquid conductivity, we increase the liquid conductivity without change the spatial distribution and interface. Increasing the liquid conductivity reduce the diffuse thickness, and so concentrate the charge near the interface. The consequence of this phenomenon is that Q, the convective spatial density, is decreasing. Now, if we assume another hypothesis in which we assume that the liquid conductivity is constant, but we are able to increase the spatial density and interface, the convective spatials is increasing. But in the real case, if we modify the liquid conductivity, we are also at the same time increasing the spatial density at the wall, effectively. If we increase the liquid conductivity, you permit more reaction and interface, and the rho W will increase. Classically, the convective spatial density have an evolution like that. It passes through a maximum before decreasing. To interpret this evolution is quite easy because effectively, if we consider that you are a pure liquid for me means that you are not liquid conductivity. We are not impurity in the liquid. If you are not impurity in the liquid, we are not chemical reaction and interface, so we are not transport of charge due to the cold layer. But now, if we increase, we have an infinite conductive liquid. Infinite conductive liquid means that all the charge are stick at the interface, and effectively, the density of charge is very higher, but we transport it with a very low velocity, with zero velocity, and the convective spatial charge is equal to 0. We will come back at the end of this talk on this fundamental curve. And finally, for finish my demonstration, I will introduce now the evolution versus time of the diffuse layer thickness. And for do that, it's not important. We have to consider a chemical model at the interface for introduce the current density produced at the wall. I chose for this talk to make an assumption of the corrosion model. And for corrosion model, the current density is given by this expression, and it mainly depends of two terms, K. K is the term linked to the chemical reaction occurring in interface, is linked to the kinetic of the chemical reaction occurring in interface. And we have a second term linked to the difference between the spatial density at the wall for an infinite electrical level layer, for a fully developed electrical level layer, minus the situation optical level layer at a distance from the wall, from the entry of the duct. So in this consideration, this means that if we are at before the duct, we suppose that we have no charge because we have not contact between the solid and the liquid. At the entry of the duct, the electrical level layer has not time to be developed, so it's quite equal to 0. And so the current density is maximum. Along the duct, the electrical level layer takes time to be developed. We have a partially developed electrical level layer. The difference of the spatial density between the electrical level layer fully developed is lower, and the current density is lower. If you progress in the duct, for an infinite duct at the end of this one, for example, the electrical level layer is probably fully developed at the end of the duct, and the whole current density is become to 0. Considering this hypothesis, we are able to determine the current density produced at the interface along the length of the duct, the streaming current along the length of the duct, and the spatial distribution along this one. The spatial distribution of diffuse layer is controlled by two terms. A distribution term, so you see exactly the distribution of diffuse layer fully developed, and also a temporal term, which is controlled by the ratio Z sur UM. This is only the time contact between the liquid in the duct, in the solid, in comparison to K, the dynamic time constant of chemical reaction occurring at the interface. So in this context, what is the problematic? What is the effect of the fluidification in electrical engineering? So let's consider a duct. This duct is full of liquid, and we want to impose a liquid flow. So according the phenomenon occurring on the interface, the chemical reaction interface, the wall current, the density is maximum at the entry and reduced progressively along the length of the duct. So typically we have this, so the charge is maximum, the charge is minimum in the liquid here, but the production of charge is maximum, and progressively we increase the density of charge on the liquid and create less charge at the interface. Two situations can occur at this time. The first situation, we consider a conductive duct rounded. This one, so we impose the liquid flow. Sorry. Come back, sorry. So we impose the liquid flow. The liquid charge from the electrical barrier is transport in the reservoir, but the opposite charge in the solid, which creates at the interface, can leak to the ground due to this connection. Now, if we change the dielectric material, the conductive material by dielectric material, or if we consider conductive pipe but not insulated, the liquid charge still to be conveyed by the flow, but at the same time, the opposite charge, the negative charge in the solid, are trapped in the solid. The local potential can increase, and the potential could be enough sometime to produce some electrostatic discharges. It was one of the problems, one of the hazards due to fluidification in electrical engineering. This is typically the situation that we will find in electrical engineering application, like in light power transformer. Light power transformer, what is it? In complete summary, we have a copper wire supported by cardboard pressboard sheet. Due to the current, we control the temperature by inducing a liquid flow, dielectric liquid flow, the oil. The circulation of the oil on the pressboard surface produces the fluidification phenomenon. And effectively, locally, we have an accumulation of solid charge, the accumulation which induces local potential. We can produce electrostatic discharge, like we can watch on this figure. And this electrostatic discharge gets reduced the reliability and creates some failure on some transformer. It is an important problematic that we can find in the electric application. Other situation that we will find is another application, for like in electric powertrain, with the interface of perfluorohexane on epoxy, but also in stainless steel materials. Other situation we can find these problematics, it is a link to the copper wire. If we have a cable, so a cable, we have the wire, which is inserted in some dielectric materials. For give the form of dielectric material, it is made by extrusion. Extrusion means that the polymer is melting by temperature. We impose a pressure from a needle to take its form, and during this circulation, some electrical label is produced. One part of the charge can be trapped in the materials and modifying the electric charge distribution, modify the electric field during during the life of the cable, which limit its durability. But why not only a bad idea of rectification? Rectification could be also electrical label could give some interest for electrical engineering because it allows to develop as we call the electrostatic pump, which is based on the electrophoresis phenomenon, which is based on electrical label, but also it can have an interest for the supercapacity, in which supercapacity are built on a principle of electrical label. So for electrical engineering, it's very important to have an idea of electrical label, which will mainly depend on the all liquid-solid couples. And so it means that we need to have an information about the spread charge distribution or the zeta potential measurement. We need to have information by measurement. We need to have also information about the Paillat. The Paillat is only independent of liquid property. It could be determined in which we have the liquid permittivity, the liquid conductivity, the ionic diffusion coefficient. This parameter could be joined by measuring by impedance spectroscopy. But for the spread charge density and zeta, we have to make some specific measurement to do it. One of the possibilities that we have is use a zeta meter. Zeta meter is commonly used by electrical engineering. The principle of zeta meter is to have some particles which is in the liquid. Due to the electrical label around the particles, and if we impose electric field, we can create a movement of the particles. By measuring the velocity of the particle, we are able to determine the zeta potential. This measurement is not sensitive for the electric liquid. It's working for conductive liquid, for aqueous solution, but not with the electric liquid. For the electric liquid, we use measurement coming from, to make the measurement by fluidification phenomenon, and specifically by measuring the streaming current. So we consider the setup classically, which we have an inlet reservoir, we have an outlet reservoir, the duct, and we impose a liquid flow from the duct through measuring the fluidification current in the outlet reservoir. This measurement is made for different flow rate. Different consideration is necessary to make to be sure the measurement will be okay. First, at the entry of the duct, we have to be sure that there is no charge in the liquid, but no electrical label modify the charge in the liquid. For do that, it's important to have a relaxation vessel at the entry of the duct in which the liquid flow could be considered equal to 0. For the measuring of the streaming current, the outlet reservoir must be insulated from ground, but insulated also from the duct. So two situations can occur. The first situation, if the duct is conductive, between the duct and the outlet reservoir, we may introduce a flange, a dielectric flange, which allows to insulate the reservoir. But the difficulty of this flange is which flange did not introduce some more charge due to the fluidification. The sizing of this flange is very difficult to determine. Other situation is that in this case we have a dielectric materials. If we have a dielectric materials, we have no problem with ventilation, but the difficulties is coming from this dielectric material because during the liquid flow, this one accumulates of charge, its potential increase, and which solid charge try to leak in the ground direction, in upstream and downstream. This one part of the charge could be neutralized, one part of the charge coming from the fluidification. For be sure to limit this effect, we have to introduce between the dielectric duct and the reservoir a conductive ring, which allows to catch only the leaky charge coming from the solid without to catch the liquid charge flowing. We can have another design of the setup given by this figure, in which at this time we have the duct, but the duct is not in contact with the reservoir. We impose a liquid flow which fall in the air in the relaxation vessel. So we have not contact between the reservoir and the duct, but it's more easier to develop, to set up, but we have some difficulties in terms of the relative liquid, which can give some problem, but also it is a one-shot measurement because when the liquid flow in the air, it could be contaminated by the different impurity in the air. So by using this different setup, the goal of this measurement is to measure the fluidification versus different flow rate. We impose usually a laminar flow rate. Typically, I remind the expression of streaming current, and we make some measurement for different flow rate. Two situations for determine the spatial density at the wall, in case, the dynamic time constant or the chemical reaction occurring at the interface. Two situations can occur. The first situation is typically what we'll observe if we use conductive liquid. We have typically here an evolution of the streaming current versus the time for different liquid flow rate. Without flow, the current is equal to 0. When we impose the liquid flow, the current reaches a steady value, which mainly depends on the flow that we impose. If we determine this steady value versus the liquid flow rate, this one is directly proportional to the streaming current. This means that at the end of the duct, the diffuse layer is fully developed, and directly you can determine the spatial density at the wall. For the electric liquid, the measurement is quite different because most of the time the diffuse layer is not fully developed at the exit of the duct. And it will be observed with the current measurement. Effectively, we have here a current measured with heptane, for example. So the streaming current, negative streaming current versus time for different liquid flow rate. And when we make a measurement with the electric liquid, we will observe a current which passes through a maximum value in an absolute value, before come back to a lower value. When I study this stabilized value versus the liquid flow rate, we have typically an evolution like that, which could be representative of the streaming current evolution that we will describe more later. It depends on the spatial density of K. By interpolation of the measurement, you can determine these two parameters. But the problem that you have, it will have an equation with two parameters. It could give some interrogation about the precision of the measurement and the unicity. Another way could be possible in this context to determine the spatial density is using, I come back, this maximum value. This maximum value represents the transport of the charge of the diffuse layer developed when between two consecutive liquid flows. If I take a long time between two consecutive liquid flow, the contact of solid liquid is higher, and we have the opportunity to create more charge in the electrical double layer. If we control this time between two consecutive, we will control the magnitude of this peak. So it's typically this measurement which is due. We control the time between two consecutive times, and we study the magnitude of this peak. By studying the magnitude of this peak, we have typically this behavior in which, for the study value, is described the electrical level layer fully developed, in which allow to be able to determine the spatial density at the wall. So with this measurement, we are able to measure different electrical level layer for different couples. So we have some example of measurement we have made at the laboratory. So for solid and the liquid, we have some dielectric solid, we have some conductive solid, we have some liquid conductive liquid, and also the electric liquid, in which we have also the conductivity and the spatial density. Look that the spatial density evaluates according to a very large scale, mainly depend on the liquid conductivity. Just a few words about the Van der Meen curve that I had discussed before. We are measuring versus the liquid conductivity we have studied heptane in which we are adding some additives. It is on the low-watt. And according the liquid conductivity, according the concentration of ions we introduce, we determine the spatial density. Not to that, the spatial density increase effectively according to liquid conductivity. And this is important to remind of one of the measurement proposed by Van der Meen. Van der Meen have shown that the convective spatial density versus the liquid conductivity evaluates like that. It is effectively linked to the effect, opposite effect of the liquid conductivity, in which increase the liquid conductivity effectively increase the spatial density at the interface, but at the same time reduce diffuse effectiveness. This fundamental curve is very sensitive for electrical application. Effectively, in the past, we'll consider that adding some antistatic additive in the electric materials save the problematic for electrostatic hazard. But if we look, it's not so evident like that because according to concentration, the risk could be measured or reducing according to concentration. So it's important to be careful of that. It's not so evident to have a solution to limit the risk by adding some additive. So only for finish my presentation, I will introduce two alternative measurements of electrical barrier that has been developed more recently. The first one is proposed by a Grenoble laboratory or an MIT. They're using the Kerr effect measurement. Kerr effect is a property of some liquid of birefringence. And by studying the image by refringence, we are able to determine the spatial density. This system is not efficient for the electric liquid at this time. Another measurement has been proposed at this time is the measurement by stimuli. It's measurement coming from spatial measurement but in solid, which are transport in the liquid. And the idea of a measurement is to impose a stimuli of anticoldable layer, and this stimuli change the equilibrium and produce electrical signal, and the analysis of the electrical signal permit to determine the spatial distribution. Some measurement, some stimuli have been studied at this time using temperature step, electrical pulse, or also pressure wave. I think I have finished in time, and I'm very pleased to present my presentation. And if you have some questions, don't hesitate.
Thank you, Thierry. Thank you very much for your presentation. It has combined theoretical aspects and practical situations, and you show us that no technical or scientific problem is never simple.
No, sure.
And intuitions always fail. So the last question about antistatic agents in liquids is quite surprising. So you try to solve a problem and you increase the problem. So very, very nice. You can write your question. By the moment, we don't have one question. I just answered one question by Simon about the availability of the presentation, and I remind you that it will be published at the YouTube channel. So until we wait for any attendant to raise a question, I have one question for you, Thierry. If one consider in a practical application in a process industry, and you want to know if your liquid is charging into a pipe, what measures you can do from outside the pipe, or how can you assess if you are having this problem in a part of your process? Because you show very scientific and calibrated, let's say, measurements, but in practical application for detection, do you have any proposal?
For prevent electrostatic hazard,
Yeah.
first, one the way is usually to be sure that for conductive liquid, for conductive materials is grounded. It's the first situation. You need to be sure that all the dielectric material, conductive material is grounded. But for dielectric material, it's quite difficult. You have to limit the potential by using, propose some way of leakage, charge leakage. And also the possibility is to effectively It shows couples, because the electrostatic is a problem of couples. It's not a problem of liquids, it's not a problem of solid, it's a problem of couples. You have to show the couples which limit the charge production and interface.
Okay. There's a question. Jim Phillips, thank you for your question. He asked, in your last point, I understood that applying a proactive static charge can reduce charge buildup in the liquid. Are there industrial solutions that apply this concept? Is there any commercial solution? Or?
Yeah. The problem that we have not a solution for all the different situations. The solution must be we may depend on the problematic that we have. Using oil, using gasoline did not give the same situation, does not permit to use the same additive for limit to hazard. So no, the problematic is that for all the situation, we need a solution, adapt solution. So it's not like a cooking in which we have a solution we could be apply for all the situation. It does not exist, but we may study all the situation or different couple for have propose a solution.
Okay. Okay. Thank you, Jim. So maybe we can move to the next presentation, and probably we can take questions again at the end of the webinar.
Okay.
If any. Thank you again, Thierry, for your effort in presenting and working on this webinar. Very, very interesting. Now we are moving to Dr. Jeremy Smallwood presentation. Let me share. Jeremy is he designed electronic instruments and before completing his PhD in electrostatic discharge and ignition studies. He runs his own company, Electrostatic Solution Ltd, providing electrostatic consultancy, training, and R&D service. He works with British and IEC standards, and he received a lot of awards. In 2010, the ESG Association Industry Pioneer Award. In 2017, the International Fellow Award. And more recently, in 2022, he received the Stig Lundquist Award at the Conference on Electrostatics 2022. Jeremy, sorry, I didn't share. The floor is yours. You can start your presentation. I will stop sharing my screen.
Thank you, Pedro. I shall try and share my screen now.
Yeah.
Do you see it?
Yeah, it's okay.
Good. Okay, thank you to Thierry for his interesting presentation, and this one will be rather different because I will be attempting to show you in quite simple terms how to understand the electrostatic risks, and to talk a little bit about standard recommendations, and also from my experience, to see how sometimes things go wrong in unexpected ways in real life. And I hope you will find it a simple and pragmatic presentation for the most part. So first of all, a little video, and this is quite a well-known video now. It's quite old, but nevertheless shows us very nicely how things can go wrong. This was taken on CCTV in a petrol forecourt in the United States, I believe. And there they had the possibility to take the fueling nozzle and leave your car fueling and then go off and do something else whilst the fuel was running, and then come back to it. And we shall see what happens in this case. I often wonder if the lady knows that she is such a star. She does such a nice demonstration of how things can go wrong. So what she does is she goes and sits in the car and shuffles around in the seat, and she charges herself up with static electricity Many of us have experienced the fact of getting out of a car and then touching the car and getting a shock. Well, instead of getting a static shock, she gets a different type of shock when she ignites the fuel vapor as it comes out of the car. Now, many people are familiar with what we call the fire triangle. To get a fire, you need to have fuel, and you also need to have some oxidizer. Very often that's air. And in the case of static electricity, if we get an electrostatic discharge and we have the right fuel air mixture, we will get a fire or we'll get an explosion. This is quite well known. And of course, the fuel could be vapors. It could also in industrial processes be dusts. It could be droplets of liquid in a mist form, or it could be a mixture of dusts, vapors, or other materials. And usually the fuel is part of our operation. It's the material one of the materials which we are handling as we do our industrial process. Often air is the oxidant, but in some processes, of course, we can have other oxidants around other than air. So flammable liquids are typically what we are concerned about because they produce flammable atmospheres. And the flash point approximates the minimum temperature at which the flammable atmosphere occurs, although the standards say to assume that you could get a flammable atmosphere 5 to 10 degrees C less, and that gives you some sort of safety margin. Now, as we'll see in a minute, the lower flash point material can give a fuel-rich mixture, and that won't necessarily ignite very easily, but don't necessarily rely on that characteristic, because in any particular situation, you can get very great variations in the mixtures that you get of fuel and air. And so you could have more air in the mixture than you would expect. The mixture might be much more unsaturated and more flammable than expected. Flammable atmosphere could also come from the residues of liquid or vapor from earlier operations. So, for example, if you have changed the type of material in a tanker and replaced a more volatile material with a less volatile material, there may still be some residue of the volatile material in there, which gives you a flammable atmosphere, even though the main material in the tank is not so ignitable. And in fact, the 60079-32-1 document, which I will be referring to a lot in this presentation, says that a high proportion of road tanker fires have been associated with switch loading. That's switching between a high flashpoint material like diesel and a tank which used to contain a low flashpoint material like gasoline. So this refers also to Annex C of 60079-32-1. This is an IEC document, and I will be referring to it throughout this presentation. Now, one useful diagram to help us understand this is here. Let me just see if I can make my pointer into a laser pointer. Yeah, here we go. So this lower part of the graph is the fuel concentration in air. So here down this end we have a lot of air and not very much fuel, and up this area we have a lot of fuel and not very much air. And we need a certain amount of energy to ignite the fuel if we are trying to ignite it, and we call that the ignition energy. And so this is the energy axis here. And we find that as the amount of fuel in the air comes from a very small amount, we pass through the lower flammable limit, which is close to the flash point. And then the amount of energy that we require to ignite the mixture drops and drops and drops until it reaches a minimum there. This is called the minimum ignition energy. And then if we keep adding more fuel, then we find that the energy required to ignite the mixture starts to go up again. This is a rich mixture in this area, and this is a lean mixture with too much air and not enough fuel in this area. Here, as I said, we have the minimum ignition energy, and it's the optimum mixture for ignition purposes of fuel in air. Now, interestingly enough, this is around about 15 degrees C above the flash point. And so one of the things that we can learn from this is that if our ambient temperature is, for example, 20 degrees C, then we can expect that the most easily ignited flammable mixtures are going to be from liquids which have flash point around about 0 degrees, 5 degrees, that sort of area. And there are quite a lot of common types of solvent, for example, which have a flash point in that area. Going for a solvent which has a much lower flash point, paradoxically would actually make it less likely that you get an ignition by electrostatic discharges, because the ignition energy would be very much higher for a rich mixture. On the other hand, a high flash point material would have a very lean mixture, and so would be difficult to ignite for that reason also. So we talked about the minimum ignition energy. The theory is that to ignite a flammable mixture, we need enough energy to exceed the material minimum ignition energy. Now, different flammable mixtures have different MIE, and a lot of them are around about 0.2 of a millijoule, up to a few millijoules. Some can be a little bit smaller than that, around about 0.1, something like that. But some very low MIE materials are also found in processes, things like hydrogen air mixture or ethylene air mixture or oxygenated mixtures. And those take very little energy and take only a very small electrostatic discharge to ignite them. I mentioned already that for a liquid, the MIE is often between about 10 to 20 degrees C above the flash point. So an example of the material which might be more difficult to handle because of that is toluene, and we might expect to see more electrostatic ignitions in a material like that because of its flash point. So how does static electricity occur? Well, already Thierry has told us a lot about this in the case of liquids, but I'm going to generalize this explanation and say that every material is made up of electrostatic charges. We know that from school physics. We have materials made out of atoms. Every atom has positive and negative charges. And when two materials come together, some of the charges move from one material to the other. And generally, we are left with one material which has positive charge and one material which has negative charge. And that can happen in liquids, it can happen in solids, and it can happen in processes, pipes or containers in the process. Now I'm going to give a very simple explanation of how static electricity builds up. And I'm going to give it in two ways. I'm going to talk about it, simple circuits, in a moment. And before that, I'm going to talk about an analogy here. It's rather like my bathroom sink. My bathroom sink might have a certain amount of water in it. The water disappears down through the plug hole and is introduced through the tap. And I might see a level of water in the bathroom sink, depending on what is happening with water passing through the plug hole or through the tap. And we can think of the electrostatic charge as being rather like the water in this simple bathroom sink. And if the electrostatic charge it can get away quickly and it's not generated very quickly, then we never see the charge build up, in the same way as if the water can get away quickly through the plug hole and we only have a small amount of water coming in through the tap, we don't see water build up in the bathroom sink. So if charge is dissipated faster than it's generated, then we don't see static electricity build up. On the other hand, if charge is generated or accumulates faster than it's dissipated, then we get build up. Then we can get a situation where electrostatic discharge can occur. Now, I used to be an electronics engineer, so I like simple circuits, but even electricians, electronics engineers, and many other people know Ohm's law. Ohm's law says that the voltage in a circuit is given by the current times the electrical resistance. Now, static charge generation, or separation more correctly, is rather like generating electrical current. Charge, of course, flowing of charge is an electrical current. So we generate static electricity, or we separate it, I should say, and it tries to get back together through some circuit, and that circuit has a resistance. Now, we will get a voltage building up because of that. We can see that from Ohm's law. And the voltage that we get will depend on the current, and it'll depend on the resistance. Now, if, for example, I say that my current that I'm generating is 10 nanoamps, which is 10 thousandths of a millionth of an amp, which is a very small electrical current, then we might not expect it to do very much. But if this resistance is a gigohm, that's 1,000 megohms, we would see a voltage of 10 volts build up. We probably would not notice that in the real world. But on the other hand, if we have a resistance here, which is 100 gigohms instead, then with 10 nanoamps, we start to see a voltage of 1,000 volts build up. And we would certainly start to notice that. And if we have a higher resistance level than that, we will have a higher voltage, maybe 10,000 volts, maybe more. So one thing we can easily conclude from this is that high resistance in materials leads to high voltages when we generate static electricity. And the high resistance materials in effect prevent the charge moving away. And what are these materials? Well, they're things like plastics and engineering plastics, things like glass, things like rubber. And high resistance materials tend to give high charge buildup, tend to give high voltages. And we must be very careful with these materials in hazard zones where we have flammable atmospheres, because they can set up the situation in which we can get electrostatic discharges for various reasons. Now, other materials which have a lower resistance, and I'm going to call them conductors or dissipative materials, these allow charge to move away if they have a path through which the charge can move. And we call that grounding or earthing. And so these other materials which have lower resistance allow the charge to move away and stop the charge building up. And of course, we're talking about things like metals, but also things like water. Water has a low enough resistance to let the charge move around quickly enough to prevent it building up in many cases. And actually, many of the other things in this photograph do as well. The bench mat here is actually one used in the electronics industry for preventing static charge buildup. The plastic tote box there is actually an ESD grade of plastic, which is specially designed to be low enough resistance so we don't get charge buildup, again, for the electronics industry. Now, why has my piece of paper got maybe or maybe not written on it? Well, because materials like paper might be an insulator or might be a conductor or a dissipative material from my point of view. It depends on the characteristics of the material. It depends on things like the water content and other factors. So just saying the word paper doesn't tell me enough about the material to know what its characteristics are. So just that last fine point, conductors and dissipative materials have low and intermediate resistance, but they must be grounded in order to give the path for the charge to move away. Well, what is grounding? Well, it's the provision of a path for the electrical charge to move away. we can do it in two ways. We can either provide wires, or very conveniently, in many cases, we can do it through materials which are conductive enough to allow the charge to flow away. But one thing we can say is that in order to work, there usually must be a continuous conductive path from the source of the static charge all the way through to Earth, so the charge can drain away. Otherwise, like a chain is useless if a link is missing, and the drain of my bathroom sink is useless if the bathroom sink drain is blocked or the plug is in the plug hole. And similarly, if there is a break in the conductive path to Earth, the charge cannot get away, and we have the possibility of charge buildup. Now, one thing we must always remember is that an insulating material or very high resistance material cannot be grounded very successfully because the charge cannot move around in the material to the ground wire. And so grounding an insulator often doesn't work, although the level of resistance that we're talking about has a big effect on this. And so we have to temper that with understanding the individual situation. Now, one thing more I'm going to talk about in terms of theory is charge storage. In order to create an electrostatic discharge, usually we have to store charge. And we have a very simple relationship between the voltage and the charge. Here we have C, capacitance, times voltage is Q, charge. And so we see that the voltage is proportional to the charge. Now, one of the interesting things that we find there is that if the, sorry, I thought it was going to be on this slide. If the capacitance varies, then the voltage will vary if we have the same amount of charge. Now, in the real world, capacitance and charge storage is very variable, and you change the circumstances and the capacitance changes and the voltage will change. And so you can go from the situation that you have low voltage to the situation that you have high voltage very quickly. And in fact, this is what happened when the lady got out of the car, because when she was sitting in the car, she generated charge on her body by sitting on the car seat, but that was a high capacitance situation, and so her body voltage was very low. But when she got out of the car, she went from a high capacitance situation to a low capacitance situation, and the body voltage went very high, probably to over 10,000 volts. That would not be uncommon. And so that's why when she touched the fueling nozzle, she got a spark and she ignited the petrol air mixture. Now, there's one thing here that I'd like to bring out, which is related to both charge storage and resistance. If you have an electronics engineer and they see a circuit like this, where you have capacitance and resistance in parallel, they say, we have a time constant here. And if my capacitance is charged up and the current stops flowing, then from the source, then the voltage will drop as the current flows through the resistance, and it'll take a certain time to do that. And the resistance and the capacitance govern the time that it will take. And in fact, there's a very simple calculation in theory which says that the time that it will take to drop to 37% of its initial value is given by the product of the resistance times the capacitance. And within this is time, the time constant, or the decay time. And in fact, if we wait for 3 times the decay time, there's very little charge left. And so we can now say a number of different things based on this circuit. We can say we store charge. The higher the capacitance, the longer we will store the charge. The higher the resistance, the longer we will store the charge. And high resistance gives us 2 things. It gives us high voltages, and it also gives us long charge decay times, and we store the charge for much longer. So there's 2 good reasons why we don't really want to have high resistance materials in our process if static electricity is a concern, and that is because we will get high voltages, and we will store charge for a long time. Now, there's one other thing about static electricity and how it works, which I'd like to show you. It's difficult to explain and much easier to see, and so I've got a little video which I hope will help. Now, here I've got a metal plate, and that metal plate is mounted on an insulating mount. It's acrylic, which has a very, very high resistance, well over 1,000,000 megohms. And so the plate with no path to ground will store charge for a very long time. Now, I do have a ground here, wire down here, which I can clip onto it to get rid of the charge if I want to. But I'm monitoring the voltage on the metal plate using this sensor, and that's connected through this to this electrostatic voltmeter here. The other thing that I have here is an ESD detector, ESD, electrostatic discharge. And this machine basically goes beep and flashes when it detects an ESD in the area. Now, I've switched the sound off so you won't hear it, but you should see it if we get ESD. And what I'm going to do is I'm going to, without touching the metal plate, I'm going to cause a voltage to be on it by bringing up an insulator. Let's see what happens. See if my video works. So my insulator here is a block of polystyrene, and you can see that when it brought it up, the voltage on the metal plate went up to about 3 and a bit thousand volts. And I didn't touch the plate. Now I touch the plate and I got an electrostatic discharge. When I take my insulator away, I've left the plate with about 3,500 volts on it, and I can get an electrostatic discharge again. And I can go on and on doing that, making discharge after discharge by just moving my block of plastic around and touching the metal plate. So you can see if this sort of thing happened in your process, this could be a really significant ignition risk. And you could see perhaps how easily that it can happen in a process. Now I'm going to just contrast this by adding an earth wire. And with my earth wire in place, the voltage on the metal plate stays 0. And when I touch the metal plate, I don't get an electrostatic discharge. So this little video shows us, firstly, that there is a risk in having an isolated, that is ungrounded metal item or conductor. We can generate electrostatic discharges, and we can set up the conditions very easily for getting an electrostatic discharge, not by touching the metal plate, but just by bringing a charged insulator nearby. And that's one of the reasons that I really worry about insulators in areas where I don't want to have electrostatic discharges. Okay. So just summarizing and talking about materials rather than circuits. In materials, we talk about resistivity, which we often give the name ρ, the symbol ρ, rather than resistance, which we give the symbol R. And in liquids, we, just to confuse ourselves, give the conductivity, which is the inverse of resistivity. But nevertheless, we're talking about the same thing. We're talking about the electrical resistance of the material. Low conductivity, of course, is high resistivity. So a low conductivity material will give the same results as the high resistivity material. Now, in material terms, I talk about permittivity rather than capacitance. But what we're talking about in both cases is charge storage. And in both cases, the charge decay time is dependent on the resistance and capacitance, or resistivity and conductivity, or the conductivity and the permittivity. In liquids, this is known as the relaxation time. It's the time it takes for the static charge on the liquid to dissipate. Just to summarize, with high resistance, low conductivity, insulating materials, high voltages are produced. The voltages can stay for long periods. Now, we will see that brush discharges can occur from insulator surfaces, and conductors can become isolated, that is, not grounded, and voltages can appear on ungrounded conductors, either by triboelectrification, that's the process that Thierry was talking about, by rubbing or by liquid passing alongside them, or by induction, which was the subject of my little video. And if we have an ungrounded conductor at high voltage, we can get spark type electrostatic discharges, and we can ignite flammable materials, a lot of them, either using brush discharges from insulators or sparks from ungrounded conductors. There are other types of discharge as well we can get in different circumstances. Now, again, this is all very much summarized in my slide, and there's a lot more information on it in the 6079-32-1 standard. So I really do recommend if you have an industrial process and you want to control static electricity, that you buy yourself a copy of the IEC 6079-32-1 and use it as a reference for your process, because it contains a lot of very useful information. But moving on, we have various different types of electrostatic discharges. I've talked about spark discharges. Those happen between two conductors. Now, those can ignite gas mixtures or dusts. If the ignition energy of the gas mixture or dust is less than the minimum, the energy available in the spark. We have another type of discharge called a propagating brush discharge, which can happen if you have an insulator backed by a conductor. And again, they can ignite gas mixtures and dusts. And I won't say much more about that, but they're very, very strong electrostatic discharge. The type of discharge which we normally get from insulators in the absence of a conductor are called brush discharges, and they can certainly ignite many gas mixtures, but generally speaking can't ignite dust clouds. In certain circumstances, we can get other types of discharges like cone discharges, which happen in silos with pellets of insulating material. I don't propose to say anything more about that, but we can ignite gas mixtures and low minimum ignition energy dust with those. And then finally, there's a type of corona discharge, which is a type of electrostatic discharge which you can get from sharp edges in high electrostatic fields. And those are actually quite useful. They don't normally ignite things, but you can use them to neutralize electrostatic charge in an item called an ionizer. And so that can be used in certain industrial processes to reduce electrostatic charge. There are other sorts of discharges that can happen, but that's as far as I'll go in this presentation. So you can see here an example of a insulating material which can become highly charged. In this case, it's polythene packaging, and in fact, we've got more insulators underneath it. We've got some polymer containers, and all these things can get highly charged when handling, and we can get brush discharges from those. Other materials like rubber, and in fact, low conductivity hydrocarbon liquids can also be a source of brush discharges. Now, moving on to talk of spark discharges from conductors. What are the sort of conductors we might have around in the environment? Well, we can have anything from very small size to large size. Small size might be bolts or small metal items, drink cans, small containers, and you can see here I've listed the approximate capacitance range of different types of items, buckets and containers, larger containers here. And one of the things that you'll see is that as the size of the container or the size of the metal item goes up, then the capacitance goes up. And actually the amount of energy that can be stored and available for an electrostatic discharge goes up as well. People here, we're conductors of electricity, and we have capacitance often in the range around about 80 to 300 picofarads. Our capacitance typically changes with every movement. Cars and vehicles have much higher capacitance. Well, they're much bigger objects, aren't they? And reaction vessels can have quite high capacitance as well. And you can see in this view of a storage area that we have a lot of different conductive items here, conductive containers, and each one of those, if they were isolated from Earth, could be the source of a spark discharge. And in fact, I have seen scenarios in which that has occurred. So possible ignition sources include things like, let's take the example of a drinks can. Not a very big metal item, but might have capacitance of around about 10 or 11 picofarads. And it would probably need around about 6,000 volts on it to have enough voltage for ignition. 6,000 volts sounds like a lot of voltage, but in electrostatic terms, it isn't. It's worth knowing that a smaller metal part would need a higher voltage, and a larger metal part might need a lowered voltage. Now, we can calculate the energy on a discharge from a metal object if we know the voltage and we know the capacitance. Simple formula, energy is a half times the capacitance times the voltage squared. Another example, human body has capacitance around about 80 to 300 picofarads. Now we know we feel static shocks from time to time, but actually we don't feel static shocks until our body voltage goes above 2000 volts. Now, if we have a capacitance of around about 100 picofarads and our body voltage is around about 2000 volts, then we probably have the energy on our body of around about 0.2 millijoules, which is around about the energy where we can start to worry about igniting things. For various reasons, it doesn't happen quite like that in the real world, and we probably need a higher voltage than that. But nevertheless, this is how you start to look at risk and how you start to evaluate risk. Now, here's an interesting isolated conductor, a bucket, plastic bucket. It's got a metal handle, and in fact, it's got a plastic part there to make it easier for me to carry it. Now, it's the sort of thing you might use in your process without thinking about it. But actually, flash fires have happened by people running a flammable liquid, a low conductivity, high resistance flammable liquid into a bucket like this and getting induced voltages on the metal part, and then at some stage the metal part sparks over to some grounded object, which might be the person who's carrying it, and then that spark can cause ignition of the flammable vapor. It has happened. So what do we do to prevent ESD risks? Well, first of all, we need to identify and control the zones of flammable atmosphere. If we haven't got a flammable atmosphere, of course, we don't have an ignition risk. And so the first thing to do is to see if we can remove the fuel or control it. And as likely as not, that may not be possible because the fuel is likely to be what we want in our process. But in some cases, we might have to make it less flammable by removing the air, by inerting, either with carbon dioxide or nitrogen or something else like that. And of course, the third thing which we might want to do, probably will want to do, is to eliminate the ESD source. In principle, it's simple. What we need to do is avoid insulators that could charge up and be the source of discharges, brush discharges. We want to avoid them because they can induce voltages on isolated metal parts. They can be the source of brush discharges. And in fact, the 60079-321-1 guidance tells us that if the insulator is smaller than a certain area, we probably don't have to worry about it. I say probably because it's up to a limit. It depends. All these things are based on certain assumptions, and for the most part, the assumptions are correct, but sometimes not. But it's worthwhile seeing the guidance of 60079-32-1. What else do we do? Well, we avoid having metal-backed insulators because we want to avoid propagating brush discharges, particularly where we have strong charge-generating mechanisms. Insulators can also prevent conductors being grounded. That's another reason we want to prevent insulators or control insulators in our process. The insulators could, of course, be process materials, which could be liquids, or they could be solids or powders or dusts. They could be packaging, they could be tools, they could be equipment, they could be clothing, they could be parts of PPE. And again, reference 60079-32-1 on all these items because it has a lot of interesting things to say. The other thing we need to do is to ground all conductors and dissipative materials. An ungrounded conductor is an ESD risk because it can charge up by induction or by triboelectrification, that's charging by rubbing. And a charged conductor can be the source of a spark. Conductors and dissipative materials, of course, can include metal parts of a process or metal parts of tools or metal parts of PPE. It could be liquid parts of a process, for example, water or alcohol or some other types of process materials. And very importantly, it could also be people. Got a picture here. What is this? This is an ungrounded conductor. Why is it ungrounded? Well, it's got a metal part, and not only does it have a rubber handle, which has a high resistance, but the guy who's wearing the glove, in this case it was me, this is a simulation of a process incident which actually happened and gave one of my customers a flash fire. The combination of the rubber handle and the glove isolated and insulated the wrench from the hand. The person's hand was grounded. If they'd been holding the metal wrench in their hand, the wrench would have been grounded through their hand. And unfortunately, the handling of the conductor caused it to charge up. And when the engineer introduced the wrench to a tap, which was wet with flammable liquid, it ignited the flammable vapor from the liquid, caused a flash fire. And fortunately, there wasn't much flammable material around, so it went out very quickly, but it didn't half give him a shock. One lesson, of course, is to never make ground connection with a flammable, with a conductor within a flammable atmosphere, because a spark could occur. And in fact, that's what happened on this case with my wrench, because my engineer was trying to adjust a tap which was grounded as part of a liquid handling pipe system.
Sorry, Jeremy, can you speed
Yeah.
up a little?
We're a bit short of time, are we? Okay.
Yeah.
I'll be quick as I can. I think we're getting through quickly. So we can ground people through materials, footwear and flooring. The standards that I told you about tells you about the resistance levels that we should get to make sure that people are well grounded. Typically where we have liquids moving, we need to think about what happens to the charge, because moving liquids, as Thierry told us, will separate charge. The question is, where does it go? We don't want it to build up. And so we'll typically have to specify bonding, that is a return path for the charge to get back together and get to Earth, so earthing as well. Now I want to have one last little experiment or experience here. This again was a recreation of something which really happened to one of my customers. They were washing a particulate material in a flask with some solvent. I think it was something like hexane. They wanted to filter the liquid from the solid, so they poured it through a funnel here. What they didn't realize is that the metal object here is an isolated conductor, and pouring the liquid through the filter created a high voltage on the filter, and in fact it sparked across to the guy's hand, and not only did it give him an electrostatic shock, but it also ignited the hexane vapor and they had a fire. Now I'm just going to go very quickly through. This is another way in which it happened. Here it's difficult to see, but we have a clip type we call a Jubilee clip. I don't know if that's the usual name for it. And the clip here is holding a polymer bag onto a pipe here. The bag is a filter bag, and so it was filtering debris out of the solvent which was coming out of the pipe, and the liquid charged and induced voltage onto the Jubilee clip, and again we got a spark and a ignition and a fire. So reducing charge buildup, just make sure you use conductive or dissipative materials where you can instead of insulating materials, and make sure conductive and dissipative materials are grounded. And to some extent, we also can ground even low conductivity liquids by having, for example, steel pipes, steel containers, and making sure they are grounded. And it'll take a long time, because with a low conductivity, high resistance liquid, the charge will take a long time to get away, but nevertheless we can lose the charge through grounding in that case. I think I'm about there. There we go. Thank you.
Thank you, Jeremy, for your nice presentation, very comprehensive presentation. So we have some questions and comments. The first one was from Dean Levitt. I think he mentioned that deionized water may not be conductive. He wrote this when you were speaking about that water can dissipate charge.
Okay. When you use words like conductor and dissipative material, the meaning varies depending on who you talk to. And in fact, in electrostatic terms, you can ground things with quite high resistances. So a lot of people will say deionized water is not a conductor, but in many situations, for my purposes, I might at least count it as a static dissipative material, if not a conductor. So there's just a word of warning about terminology there. When you use words like conductors and dissipative materials and insulators, be careful who you're talking to, because the meaning will vary from context to context.
Okay, thank you, Jeremy. I thought you can see the contact information on the screen. I'm sharing the emails of the presenters. And there are also two questions. I don't know if it's the same person, because it's anonymous attendant with no name. The first one is they say if an earthed deep pipe is used to limit the charge in a glass-lined vessel containing a steroid insulating solvent, what will be its minimum surface area necessary to have a beneficial effect? So if I understand, if you use a kind of metallic grounding to an insulating line, how much surface should you cover to have a benefit?
Could you repeat the question, please, Pedro?
if an earthed deep pipe is used, I think you clip something in a pipe. I understand this. I don't know exactly what is an earthed deep pipe. Is used to limit. I will share the screen. Maybe you can you see the question here, Jeremy?
No, I can't. You've
No,
already
you can't.
replied up.
Maybe I can
Might
paste
be
it
able to
in
Q&A.
because it's let me just one moment.
Yeah, I can see it in the Q&A actually. I
You
can
can just indicate, yeah.
Yeah.
He speaks about an earthed deep pipe is used to limit the charge in a glass-lined vessel. So
Yeah.
I understand this. The situation is a glass insulated vessel, and you use some metal
Yeah.
pieces to earth.
I have a very short answer to that. I don't know.
What's the minimum surface? Yeah.
To go more deeply into that, you'd have to look at it much more deeply, I think, before. I would be very reluctant to give a quick answer to that sort of question.
I think in some ATEX standards, they speak about a maximum surface of non-conductive materials in explosive atmospheres. It's a limitation of the surface. Maybe that can be a guidance, but I agree with you. It's not an easy answer.
It certainly, if a standard or guidance document gives useful guidance on it, then that is something that should be referred to. Yeah.
Then maybe the same person asked about brush discharge. I think this is a very long question to answer. My understanding is that once the breakdown of air is exceeded, the air becomes ionized, leading to a corona discharge. I had assumed this process would discharge the material, leaving very little residual charge to trigger any further discharge, such as brush discharge.
Okay, I mean,
Otherwise, the question is, if corona discharge, why is not saving the day? Understand?
Again, I don't have a quick answer to this one, but the thing about a brush discharge, one of the things to understand is it doesn't discharge the whole material unless it's only a very low area material. If you have a conducting material and you discharge from it in a spark, then the majority of the charge will be released into the spark from the material. But the same is not true of a insulating material and brush discharge. And one of the reasons for that is that the charge does not easily travel along or through the material itself. And so what tends to happen is you get an area which is discharged around about the site of the brush discharge, and it's not even completely discharged in that area. But and it's one of the reasons that it's called a brush discharge is you get little channels which are discharged more than others, and you get figures which are called Lichtenberg figures, which show you the sort of thing which happens. So I can't answer that any more deeply than that.
Yeah, so basically, corona discharge may help to discharge floating metals, but not insulating materials.
No, that's not quite what I said. Corona discharges can be used to neutralize charge on items. They won't neutralize all the charge on an item, generally speaking. You're usually left with a few thousand volts on the surface of the item. But a brush discharge will not completely discharge an insulating surface. On the other hand, a spark discharge will more or less completely discharge a conductor, although there may be some residual charge left on it.
Okay. Two more questions. I think that will be the two last. Again, Jim Phillips. Yeah, nice demonstration. In the demonstration, you had a charged insulator. Was there anything special about the polystyrene material? How does that become charged? Is that just a normal property of that material? Is there a way to discharge a charged insulator?
Yeah, all good questions. There's about 3 there, I think. Yes, it was a normal expanded polystyrene. It came out of a cardboard box when I received some equipment. It's the sort of thing which is used for packaging materials. How did I charge it up? I rubbed it with wool
Mhm.
cloth, probably, because that's what
Yeah.
I usually rub them with. But I could have rubbed it with many other types of material, and it becomes very, very highly charged. This is our normal experience. If you are used to unpacking equipment from boxes with expanded polystyrene in it, you know that it becomes highly charged. Is there a way to discharge it? Well, you can use an ionizer to neutralize it. And this is the use of corona discharge because type of equipment called an ionizer is designed so that it has sharp points which can produce corona discharge, which effectively sprays out the opposite polarity charge into the air around the high electrostatic field. And that charge will travel to the charges on the material and will neutralize it to some extent, not completely, but to some extent. And in many cases, in industrial processes, that is enough. In electronics industry, they are very, very fussy and they tried to reduce the charge level to very near zero, and they have to use special types of ionizers to do that, which are active devices rather than passive devices.
Okay, thank you again, Jim, for your question. And the last one, I'm sorry, there are two more, but I will only read the question from Lucas Paulo. Hi, Pedro and Jeremy. In the slide where the wrench were isolated, Jeremy wrote that you shouldn't ground equipment in explosive areas. Can you explain? Is that right, or did I understood wrong?
Right. The way that it's come over is perhaps incorrect. The conductor should be grounded. It must be grounded, but you shouldn't make contact with it. Do you see what I'm saying? It needs to already be grounded when it enters the explosive atmosphere, because you must not make contact with earth and an isolated conductor in the presence of a flammable atmosphere. And in fact, that's exactly what happened in the incident that I was recreating there. The wrench should have been grounded through the man's hand, but he wore a glove which prevented it being grounded. And so when he presented the wrench to the pipework, an ungrounded conductor made contact with the grounded pipe and electrostatic discharge occurred. Where you have an ungrounded conductor, it will probably have some voltage on it. We don't know what the voltage is, but there will probably be some voltage. If you think of it in that way, then it's a safe way to think about it.
Okay, thank you, Lucas. Yeah, I thought I was not reading the last question, but I think it's a good question for both, for Thierry and Jeremy. It's again from a anonymous attendant. So it says sometimes limiting liquid velocity in pipes, managing flammables, is an approach to avoid static discharge and consequently reduce fire explosion risk. So reduce limiting liquid velocity in pipes. Is it a valid and useful approach to limit charge?
Do you want to take this one, Thierry, or otherwise I will make a comment?
So Thierry, please, Thierry.
Yeah. Yes, effectively, if we reduce the velocity of the liquid, we limit the risk. But it mainly depends of what we need for the application. So sometimes possible, sometimes not possible. But effectively, reducing the velocity, reducing also, not also the velocity, because there is a difference between laminar and turbulent flow. Turbulent flow also increase the phenomenon. So effectively, reduce the velocity, reduce the risk, the hazards.
Good.
May I add just quickly
Yeah.
something to that? One of the things that we do in the 6079-32-1 standard is to recommend limits to liquid flow rates for various different situations. And it may be this that the person who asked the question has in mind. The reason we do this is because when we have a faster flow, usually we have higher static generation. And so if we want to limit the static generation, we specify a low flow rate.
Okay. So I think now we will finish the questions. Thank you all of you. Thank you, Jeremy and Thierry, for your effort in
Thank you
preparing
for
this presentation. I think the webinar was very interesting. Thank you all the attendants for the very interesting questions you have raised and your active participation. I don't know if Giorgio, you want to say some words before
Yes,
closing?
I just wanted to thank you all for this very nice webinar, and I want to highlight that the number of attendees until now has been reduced a little bit, but until a few minutes ago was very stable all the time. So, which means that your presentation were received with interest by all the attendees. And thank you so much. It was very nice to see theory and also practical aspects on this subject, which is not well known by many. But as you said, Pedro, I think you have a small but very well connected community. So I think that you are doing a great job in spreading the knowledge on a subject not so evident. So.
We try.
Thank you, everybody, and thank you, Martin, for being here all the time. And see you in Bologna, I hope.
Okay, thanks
See
a
you.
lot. Have a good day.